Precalculus review. When working with functions, we want to both be able to evaluate and do composition with them. Now, as a reminder, while evaluating is simply plugging numbers in, composition is where you evaluate a function with another function. The types of notation you're going to look at, for instance, would be f of 5, if you're going to plug a number into it. You may be seeing something like maybe f of x plus 3, if they wanted you to plug an expression into a function. Or with composition, they may say things like f of g of x, to say that we're going to plug the function g into the function f. So be aware and be prepared to work with either one of these styles of function notation. Now, in our first example, we'll look at functions f and g, where f of x is 2x plus 3 and g is 5 minus 5x squared. So the first one I'll try is just what would f of 7 be? And that, of course, means we'll take 7 and plug it into the input here for f. So that would look like 2 times our input 7 plus 3. And of course, when we work that out, that would be 14 plus 3, which would be 17. Here in the second example, we'll be looking at g of x plus h. So in this example, we'll be plugging an expression into the function g. So this time what happens is we'll have 5 minus our input, which in this case becomes the expression x plus h. We're going to square it. Now, to simplify this, you have to make sure that you FOIL this out. Multiply x plus h times x plus h. So this whole thing would become x squared plus 2xh plus h squared. And then, of course, we can distribute our negative, and we can write the final expression here is negative x squared minus 2xh minus h squared plus 5. Our next example explores composition. So here we can see we're plugging the function g into f. So we're basically working with the function f of x, but in place of its input, we have the entire expression here for g. So when we do this, we have, again, the main function f of x here, which is 2 times our input. And in place of that, we're going to put in a 5 minus x squared. And it's important to use parentheses. And then after that, plus 3. So as you can see, we have the 2 input plus 3 that f of x has, but we replace that input with that 5 minus x squared. Now to simplify, we'll distribute and combine like terms. So we'll get 10 minus 2x squared plus 3, or when you simplify, negative 2x squared plus 13. Now in our last example, we have another composition, but we've switched it. This time we're going to plug the function f into the function g. So which means we're going to be working with the 5 minus input squared, but we're going to put the 2x plus 3 into that. So again, g is 5 minus our input, which is f of x, 2x plus 3 squared. And again, we need to go ahead and multiply this out and combine like terms. So we have 5 minus, if we take 2x plus 3 times itself, we get 4x squared plus 12x plus 9. And then when we distribute the negative and combine like terms, we're going to get a negative 4x squared minus a 12x minus 4. Another very important area of evaluating functions is what's called the difference quotient. And this special expression is a very important aspect of calculus, especially when we start defining derivatives with limits. So we want to be able to work with the algebra of evaluating functions and simplifying them in this expression. So for example, what if we have the function, again, 2x plus 3, and we want to fully simplify that difference quotient? So that means that when we talk about the f of x plus h, that means we have to take our function and evaluate it at x plus h. So that means it's going to be 2 times our input, x plus h, plus 3. And then we want to subtract from that the original function f of x. So we'll subtract all of the functions. So you do have to use parentheses here to ensure the entire function f of x here, the 2x plus 3, is being subtracted. And then, of course, from that, we'll just divide the whole thing here by h. Now, our job in this situation is to simply, simplify the numerator as much as we can. And one thing you'll notice each time, especially with polynomials, that when you work with a difference quotient, is that as you simplify the numerator, all the terms here that don't have an h in them actually cancel out. You'll have opposites. And the only remaining terms in the numerator, because they have h in them, you can factor that out and cancel. So typically, you're done simplifying with the difference quotient when you're able to cancel or simplify the h in the bottom to go away. Now in the numerator, if we go and distribute and combine like terms, we're going to have a 2x plus 2h plus 3 minus 2x minus 3. And all that, of course, being divided by h. And again, what we can see here is that the 2x and the negative 2x, their opposites, 3 and -3 opposites, and everything without an h in it goes away. So the only terms left have h in them, so we have a 2h divided by h, and again we can reduce those h's, leaving us with 2. Let's try it again, but with a different function. Here we'll look at the function 3x squared minus 1. And again, we're going to evaluate that here in the difference quotient. So to begin, we're going to plug x plus h in first. So we want that g of x plus h, which is going to look like 3 times x plus h quantity squared minus 1. And we'll subtract from that the original function 3x squared minus 1. Divide the whole thing here by h. Okay, so if we go ahead and work out the top, we're going to get 3x squared plus 6xh plus 3h squared minus 1 minus 3x squared, and then plus 1. And just like our previous example, you'll notice every single term in the numerator that doesn't have an h in it has an opposite. So the 3x squared, the negative 3x squared cancel out. Negative 1 and positive 1 cancel out. So all we're left with then, as you can see, is going to be on the top 6xh plus the 3h squared divided by h. Now, once this is done, we can again, because all the terms have an h in the numerator, is factor that out, leaving us with 6x plus 3h, and then we'll divide by h. And of course, those we can reduce. So our final result is 6x plus 3h fully simplified. The next thing we want to discuss are the graphs of elementary functions. And we simply want to be able to recognize and understand from the equation what the graphs look like, or vice versa, knowing the graph and kind of understanding what elementary function that would come from. So the first one I just want to review with you is y equals e to the x, which is an exponential function. It does have a horizontal asymptote here of the x-axis, which means it approaches yet never gets there. So this graph is always positive, always increasing, and I should point out, does pass through this ordered pair here, 0, 1. Another elementary graph we want to look at is e to the negative x, which is essentially the same as our previous graph, but of course with a negative up here in the input, it reflects it about the y-axis. So it's still always positive, but this time always decreasing. It does always remain above the x-axis. It still has the x-axis being a horizontal asymptote, and it still passes through the ordered pair 0, 1. The graph of the natural log of x is actually the inverse of that. Right, so because the natural logarithm and the base e, right, they can become inverse functions. So we have the same kind of shape, but obviously we reflected that. So now we have a vertical asymptote, that's the y-axis, and while it never quite gets there, it does continue down indefinitely. So this increases always, and then slowly kind of becomes a little less steep. And this time again, because it's the inverse, it passes through the ordered pair 1, 0. Trigonometrically, we want to recognize the graph of sine of x. And clearly, it just makes a nice sinusoidal sort of wave, as you guys can see. The things to keep in mind, of course, are that the sine of x trigonometrically does go through the origin. The sine of 0 is 0. That's kind of a nice starting point, if you will. But, periodically, it does continually repeat. Without any other, numbers or anything else in the equation, it does have an amplitude of 1. So that means that, it goes up as a maximum value of 1 and a minimum value of -1. Cosine, of course, is identical, but of course shifted a little bit because with cosine, while we do have the same values, they happen in a little bit different places. And so while all the things are the same, except passing through the origin here, where this actually goes through the ordered pair 0, 1, since the cosine of 0 is 1. But it does have the same amplitude of 1, and so therefore it's maximized at 1 and minimized down here at -1. One of the more interesting graphs, we have 1 over x. And this is interesting just because, unlike our previous examples, this graph actually has 2 branches. It has that because there's both a vertical and a horizontal asymptote. There's a vertical asymptote here because obviously there's no way the y value can ever equal 0. And more importantly, you can't plug 0 in, so there's a vertical asymptote. So we have obviously our branch up here in the first quadrant and a branch down here in the third quadrant. The graph of y to the x is the most basic linear equation passing through the origin with a slope of 1. If we square x, now we have a parabola, a second degree function, which again passes through the origin and increases both directions. If we cube it again with an odd power, now instead of having it go up both directions, now it increases left to right. Still passing through the origin, but clearly with negative inputs, we do have negative outputs. Now let's look at a generic graph and just be able to identify some of the basic pieces. So things like roots, intercepts, and where it increases or decreases. Now roots are the places where, when you plug an x in, you get a 0. Okay, so we're looking at what x values make this, the equation that would give this graph equals 0. Well, that would be any place here that, the y value is 0, where it crosses the x-axis. So the roots would be, for instance, in this case, x equals -2, okay, x equals 0, and x equals 1. So these are the places here, as you look along, that if we were to plug it in, the y value is 0. Now, as far as intercepts, that's related, because obviously this is where it crosses an axis. However, we would also consider any y-intercept, So in this case, when we write the intercepts, they are ordered pairs because they're locations on the graph. The first one would be, of course, -2, 0. And then we have 0, 0, which serves as both an x and a y-intercept, and 1, 0. So those right here, here, and here would be those x-intercepts. Now, as far as the increasing or decreasing, we can see right away from the graph as we move left to right that it increases, then decreases, then increases, and again decreases. So there's 2 different intervals over which it increases and 2 different intervals over which it decreases. So if I was to express where that was happening, I would use interval notation. So the graph begins increasing all the way up to about, I'm going to call this -1.5. So that means it's increasing from -infinity all the way up to -1.5. And then we write union, and it begins increasing again. I'm going to call this about +1/2 up to 1. So on those 2 intervals, the graph is increasing, whereas on the other intervals, it's decreasing. So clearly from about that -1.5 all the way down here to 0.5, so we'll call that decreasing. So -1.5 to 0.5, and then everywhere after 1. For trigonometry, we do want to know the basic right triangle trigonometry. So, for example, if given a right triangle and some sides, we want to be able to calculate the 6 trigonometric functions. So as a reminder, the sine function is the opposite side of an angle divided by the hypotenuse. The cosine is the adjacent side of the angle divided by the hypotenuse. And the tangent is the opposite side divided by its adjacent. The cosecant, secant, and cotangent are the reciprocals of each of these functions. So once I know what sine is, by simplifying the reciprocal of the ratio, that gives us cosecant. And the same is true with secant and cosine, as well as cotangent and tangent. Now, in order to calculate all 6 of these, you do need to know all sides of the right triangle. So I'm going to use the Pythagorean theorem to calculate what the other side would be. So if I know the hypotenuse is 7, I know that squaring that will be equal to taking the other side, radical 5, squaring it, and that, of course, would be added to this unknown side I'm trying to find. So this is basically 49 equals 5 plus, some unknown squared. So if I subtract the 5, I get 44. And when I square root it, we're going to look for the principal root, because obviously we want a positive measurement here. And when you take the square root of 44, you can simplify that to be 2 square root of 11. Now that I know the 3 sides of my triangle, I can go ahead and just write down the ratios for sine, cosine, and tangent, as well as their reciprocals. So for sine, the opposite is the square root of 5, and the hypotenuse is 7. So that's going to be obviously what I'm going to work with there. When I look at the cosecant, we just have to flip it over. So we'll take 7 and divide it by the square root of 5. But we don't want to leave the radical on the bottom. We want to rationalize it. So we're going to simplify this to be 7 radical 5 over 5. Now for cosine, we want to do the adjacent side over the hypotenuse. So in this case, the adjacent side of the angle is 2 radical 11, and we'll divide that by the hypotenuse 7. And again, if we go ahead and flip that over, and we take 7 divided by 2 times the square root of 11, we still want to rationalize that denominator to get 7 square root of 11 over 22. Now to do the tangent, we have to take the opposite divided by the adjacent. So we'll take the square root of 5 and divide that by 2 square root of 11. Now, when we rationalize this one, of course, we're going to get the square root of 55 divided by 22. Now, the cotangent just flips that over, so you can write 22 divided by the square root of 55, but of course, we want to rationalize that to be 22 radical 55 over 55. Now, as far as knowing other angles and kind of working out in the coordinate plane, we want to know the unit circle, which really talks about knowing sine, cosine, and tangent of all 45 and multiple 30 angles all the way around. okay? Whether we talk in degrees or in radians. So where 30 degrees, of course, being pi over 6 radians, 45 degrees being pi over 4 radians, and of course 60 being pi over 3 radians. In addition to those main special angles, we also want to know the quadrantal angles where we have 0, 90, 180, and 270, or 0, pi over 2 pi, and 3 pi over 2 radians. So these ordered pairs, right, are very important to know. And as a reminder, when we talk about these values and their locations, all of the ordered pairs, the x, y's, if you will, in the coordinate plane, translate into whatever the x value is. For instance, this value right here, that would be the cosine of the angle. So again, this example I've circled, this x value, 1/2, would be the cosine of pi over 3 radians, or 60 degrees. The y value gives us the sine of the angle. So that means if I pick any y value somewhere, for instance, right here, this y value, negative radical 2 over 2, would be the sine of 5 pi over 4, or 225 degrees. In order to find the tangent, you basically, of an angle, you basically take the y value divided by the x value. Or, in terms of trig, you take the sine of the angle divided by the cosine of the angle. Now, it's sufficient to simply know sine, cosine, and tangent because you can always calculate them. And if you need a cosecant, secant, or cotangent, just find the reciprocal. So let's practice doing a couple basic evaluations. And again, this would be something you want to be able to do from memory. So if we're looking at the cosine of pi over 3 in your head, you want to kind of understand where pi over 3 is, right here at 60 degrees. And since we're looking at the cosine, we want the x value there. So in this case, the answer would be 1/2. Now, when we talk about doing, for instance, sine of pi over 4, that means we're going to be looking right here. And the sine, of course, is the y value there, which would be radical 2 over 2. Now, to do the tangent of 5 pi over 6, first off in your mind, you've got to recognize this location. But more importantly, be able to take the y value divided by the x value, right? Sine divided by cosine. So technically, you take 1/2 and divide that by negative radical 3 over 2. Now, when you simplify that, you end up with negative radical 3 over 3. Now, for the last one, we're going to be looking at the secant of 7 pi over 6. So first off, 7 pi over 6 in your mind locates here on this ordered pair. But to do secant, you want to consider what the cosine is and then flip it over. Well, the cosine is negative radical 3 over 2. So that means the secant will be its reciprocal, or negative 2 over radical 3. But of course, we want to rationalize that. So the final result would be negative 2 radical 3 over 3. For linear equations, there's many different things you always want to be able to do, especially with calculus, as we often look at things like tangent and secant lines. But just as a review of the basics, you want to be able to calculate slope, understand the relationship with parallel and perpendicular lines, and be able to write linear equations. So, as a reminder, slope is often referred to as m, but is the change in the y values, or rise, divided by the change in the x values, or the run. So it's basically the vertical change divided by the horizontal change. Now, another note, of course, is that perpendicular lines, right, they have the exact same slope. Whereas perpendicular lines, right, this symbol right here, they have opposite reciprocal slopes. So if you want to find a perpendicular slope, you take, whatever the ratio is for slope here, take the opposite sign and find its reciprocal. Now, the types of linear forms you may want to use are, whatever I guess you feel most comfortable with. Oftentimes, mx plus b, right, slope-intercept form is a pretty common one. One that we will often use in calculus because of its ease is point-slope form, where you take y minus the y value of an ordered pair on the line, and that's equal to the slope, times the quantity x minus the x value of a point found on the line. This is a nice, easy one because, unlike slope-intercept form, this only requires knowledge of the slope and one ordered pair that lies on the line. Whereas in slope-intercept form, you have to know the slope and specifically the y-intercept of the line. So both of these require a point and a slope, but this is any point, this is a specific point. Now, a third form you might see is standard form, where we have a real number times x plus a real number times y equals a real number. However, I will tell you that oftentimes this is the quickest and easiest linear form used. So looking at our first example, we want to make a line that passes through the ordered pair 2, -5, yet parallel to this line here. So I have an ordered pair, but again, I need the slope to make my equation. So what I'm going to do is I'm going to figure out what the slope of this line is and just use the same thing because I want a parallel. Now, right now, it looks to be written in standard form, and unlike the other two, you really can't see what the slope is. So if I solve for y, like in my slope-intercept form, I'll be able to visualize what the slope ought to be. So solving this equation here for y, you'll get y equals negative 1/2 x plus 3. And now I can see right away the slope of this line is negative 1/2. So that means the parallel slope that I want to use is the same, negative 1/2. So when I do the equation here, I'm going to use point slope form. So it's going to be y minus the y value, so minus the negative 5. And that will equal our slope here, negative 1/2, quantity x minus our x value. Now in our second example, we have the same idea, except we want to find the line passing through the two given points. So our job now is to use the slope formula and calculate what is the slope between them. So to do that, of course, we'll take our y value and subtract them. So I'll take the second y value minus the first one, and then take my second x value minus the first one. So on the top I get a 10, the bottom I get a 2. It looks like the slope here is 5. Now, just like before, I'm going to go ahead and use point slope form, and I'm just going to go ahead again and use the first point. It doesn't really matter which one you use, either one is fine. But again, we'll do x minus our negative 5, so y plus 5, and that's going to equal our slope 5 times the quantity x minus our x value 2. In our next two examples, we'll look at lines that are either parallel or perpendicular to the x-axis, which means they're going to be vertical or horizontal. Now, if I want to be parallel to the x-axis, that's going to be a horizontal line, okay? So that means your slope is going to be 0. And that, of course, means since you're horizontal, the only thing true about all the ordered pairs is that they share a y value. So the form of any horizontal line is simply y equals the y value. Since this line needs to pass through the ordered pair 2, negative 5, y equals negative 5 describes that. Now, if I want a line to be perpendicular to the x-axis, that means I have a vertical line. Now, that slope is undefined because you can't divide, by 0. However, to be, looking at any point, on a vertical line to be like this, they all have the same x value. So simply saying x equals whatever value they all share describes that. Since, again, I want to pass through the ordered pair 2, negative 5, x equals 2 makes that happen. The last part is going to look at simplifying. So to begin, let's look at simplifying some rational expressions. Now, obviously, when we look at this, we're going to have numerators and denominators with polynomials in them. And so what you would want to do is reduce any common factors. We need to factor and simplify as much as possible. If we're adding or subtracting, that does also mean we do need to find common denominators. Now, in our first example, we're multiplying. So we simply need to factor all the pieces as much as possible. And as we multiply the whole top together and the whole bottom together, reduce any common factor that's in both the numerator and the denominator. So first off, the 10x to the third doesn't need to be factored at all. My x squared minus 9 that I'm going to multiply times that can be factored to x plus 3 times x minus 3. In the denominator, I can factor 3 out of this expression to be 3 times x plus 3. And then when I multiply the next part here, I can actually factor a 4x out, leaving me with an x minus 3 from that quantity. Now, I've put it together in multiplication and factored everything, so I can tell right away I can reduce x plus 3 as well as x minus 3's right away. Also, the 1x down here can reduce one of the x's up here. And actually, I just realized I miswrote that. That's actually going to be x to the third. Make that a 3 there, just had to copy that down. And when you reduce that, that actually becomes x squared. So I'm going to go ahead and gather things up and see where I'm at now. On top, I have a 10 and then an x squared. On the bottom, I have a 3 and a 4, so that just gives me 12. And after I put all that together, I notice I can further simplify 10 twelfths to be 5/6. So this right here will be 5x squared over 6. Now, while this is the simplified expression for my original product here, it's important to also understand, though, that we will assume x may not be a positive or negative 3 nor 0, because even though I was able to cancel them out, to stay true to the original expression, those are numbers that would make me divide by 0, and we cannot plug them in. In our second example, we're looking at addition. So what we're going to need, of course, is common denominators. Now, to figure out common denominators, it helps to factor what we have here. Now, the first one, of course, you can't factor, so we're going to leave that alone. However, in our second denominator, I can factor an x out. Now, by doing that, I kind of see all the pieces that make up all the denominators. So in our first denominator, we have a 3 and an x. In our second denominator, we have an x and an x plus 1. Now, the common denominator is basically all the unique factors happening at their highest power. Well, the 3, the x, this x, and the x plus 1, they all happen to the first power. So power is not an issue, but I need to make sure all the unique things show up. So my common denominator that I come up with here, right, is going to have a 3 in it, okay, because that's happening. It needs to have an x in it, because we have that in each one, but also the expression x plus 1. Okay, so that makes my common denominator. Now, when I look at my first fraction, its denominator only has a 3x, which means to make my common denominator, I'm going to multiply by x plus 1, which means the numerator here of the 2 also must be multiplied by that. So from my first fraction, I have a 2, but I have to multiply it by x plus 1. Now, in the second part, as we put this together, I already, of course, have this x plus 2 in there, but looking at the given denominator x times x plus 1, it's missing a 3 to become the common denominator. So I need to multiply that x plus 2 that's already there by a 3. And from now on, we can simply distribute and combine like terms in the numerator. So here, if you look at the numerator, we're going to get a 2x plus 2 plus a 3x plus 6. And of course, we'll divide that by our common denominator. I often do not combine terms in the denominator just for ease. And oftentimes things we do with rationals necessitate not doing that with the denominator. But if I do clean up the numerator up, combine like terms, we're going to get a 5x plus 8 divided by our common denominator, 3x times x plus 1. Now let's look at what's called a complex fraction. Here we are dividing, so technically I'm going to take all the stuff in the numerator and divide it by the stuff in the denominator, and usually what you'll end up doing is taking the expression in the numerator and multiplying it by the reciprocal of the denominator. However, before we can do that, because we have things being added, we need to put them together. And like before, we need to find common denominators. So step number 1 is we need to clean up and combine the numerator and denominator into single terms. So if you look at just the numerator, we have an x as far as 1 kind of denominator, and this is the same thing as y over 1. So the common denominator for the numerator is going to be x. And of course, if you want to put that together, the 6 already has the common denominator, but you're going to have to multiply the y times x to make that be able to put together. In our denominator, again, this is over 1, so we have a y and a 1, so that's common denominator is simply going to be a y. Now, from our first fraction, x already has the common denominator, so it won't change. But when we add on the other one, the 3 needs to be multiplied by y to be put together. So now that I've combined the two fractions at the top and bottom to become single terms, right, single fractions, now because I'm dividing, I can rewrite it to be the top fraction multiplied by the reciprocal of the bottom. Okay, so what that's going to look like is we're going to have our 6 plus xy over x, and we're going to multiply that times the reciprocal of the denominator here, which is y divided by x plus 3y. So now that I'm in multiplication, I can simply multiply across the top and across the bottom. So if I simplify that, I'm going to take the 6 plus xy times y, which gives me 6y plus xy squared. And then the bottom, if I distribute the x, I'm going to get x squared plus 3xy. Now, the last thing I want to talk about is dealing with exponents. Okay, so we want to talk about the properties and be able to simplify expressions that have exponents in them. So to review, we want to look at products, quotients, powers, reciprocals, and radicals. So as far as products, what we're looking at here, of course, is the idea that you have like bases and you're multiplying them together. Okay, so for example, you have x raised to a power, and you're multiplying it times, again, the same base raised to a power. Okay, so it's important to understand with all of these, the bases are the same. It's the exponents we're working with. So when the bases are the same and you're multiplying those two like bases together, you add their exponents. So if you take x to the a times x to the b, that simplifies to be x to the sum a plus b. Now in a quotient of like bases, for instance, x raised to the a divided by x raised to the b, this is where you subtract them. So the simplified version here would be our common base x, and it's the numerator's exponent minus the denominator's exponent. So this would be a minus b. Now when we talk about powers, we mean a base raised to a power, and then we raise that to another exponent. So we basically have two exponents. And when this happens, we just multiply them together. So if you have x to the a raised to the b, that simplifies to be x raised to the a times b. Now, reciprocals come about by negative exponents. So if I have x and my exponent is negative, what that tells me is it needs to be the reciprocal. So a negative exponent means it's 1 over the base raised to that power. And once you actually find the reciprocal, the exponent now is written positively. The last is the relationship with radicals, and that's just talking about rational or fractional exponents. So if you have, a base x and you're raising it to like 1 over a, that means you're taking the 8th root of x. So anytime you have a radical, whatever the index is basically a 1 over, and that's like the denominator in a fractional exponent. So let's try a couple examples. So first one here, we have x to the third times the square root of x. So the first thing I'm going to do is rewrite the square root of x using our bottom property here to be radical, right? And change that obviously to be exponential. So we're going to take this as x to the third, and we're going to multiply that instead of radical x to the 1/2 power. Now, once I do that, I can clearly see I need to add the 3 and the 1/2 together. So when you take 3 and 1/2 and add them together, you get 7/2. Now, in our bottom example here, we have things going on in the numerator and the denominator. So while we will probably need to do some subtraction of those exponents, we want to clean up each one first and make it look exponential. So on the top, we have x squared raised to the -4th, right? So that's going to be where we multiply. 2 times -4 gives me -8. In the denominator, we have x squared, but again, we're taking the cube root of it. So when we make this exponential, remember the root part, that becomes the denominator, the power, but this already has a 2 in it. So that means it's going to have a 2 and then divided by 3. So it's x to the 2/3 power. Now again, because we're dividing, we're going to subtract the exponent. So we can take -8 minus 2/3, which will give us -26/3. Now, as far as writing x to a power, that's true. But because the exponent's negative, we can further simplify it using the reciprocal to be 1 divided by x to the 26/3.